That's sort of the counterintuitive way of doing science, falsification. The point here is, this is the standard to which creationists have been held for the past 40 years. Give us a testable prediction, is what I'm hearing from evolutionary opponents. Last fall, October, I published a book, Replacing Darwin, in which I laid out testable predictions to meet this standard. So I'll give you a specific example, drawn from some of the data I discussed in Chapter 6, applied now to birds. So there's 11,000 living bird species today. For sake of argument, let's assume within a creationist framework that they arose from a few hundred ancestors on board the ark, and at a constant rate, just to keep the math simple. I'm going to ignore those few hundred in my math and just use 11,000 because it's a nice round number. And I said earlier, divided by 4,500 years gives you an average rate of species formation of 2.4 new bird species per year. It could have been that there was a burst of speciation immediately following the flood that then tapered off to the present day. You still get an average rate, just as sort of a ballpark number, 2.4 new bird species per year. Very different then from what the evolutionary model might propose. So the modern evolutionary model says birds evolve from dinosaurs. So to get from dinosaurs to birds, you have to go through transitional forms. Dinosaurs go extinct within the evolutionary framework about 65 million years ago, but given that lag time to form modern birds, and if you look at the evolutionary literature, they typically put the origin of modern birds beginning around 35 million years ago. So let's use that number. 35 million years divided by 11,000 species gives you an average rate of one new species every 3,200 years, much slower than what I just told you. And to give you a side-by-side comparison, within 3,200 years, at the rate of species formation that I just proposed, 2.4 per year, in 3,200 years you get nearly 8,000, 7,680 new species. So there's orders of magnitude difference, thousand-fold difference between these two models. Not surprising, because we're dealing with timescales, 6,000 years, millions of years, that are orders of magnitude different as well. But the point here is this number is something you can test and try to falsify. You can do experiments on this. Now, some of my opponents have said, well, we've already done the experiments. No one's observed the formation of a new species within the last few hundred years, as long as we've been studying species. And I said, well, let's hold on a minute. When does the modern discipline of classifying life begin? Well, it begins with Carl Linnaeus. He lives in the 1700s, so roughly 300 years ago. And we have, if you look at documentation for the modern bird species, and they give the author, who's the author responsible for discovering the species, you won't get things older than Linnaeus. So the bottom line is we've discovered 11,000 new species within 300 years. We've been discovering, on average, 37 new bird species per year, much higher than the predicted rate at which species form. So really the question that we need to ask is, how many of these bird species discoveries represent, number one, either the discovery of a species that has always been in existence, but we just didn't pay attention until now, or versus number two, how many of these 11,000 species documented in the last 300 years represent bona fide new species formation? Well, how would you do that practically? Part of the practical challenge in testing this hypothesis, in evaluating that rate of 2.4 new bird species per year, is that there's anywhere from 9 to 30 different definitions of what a species is. And to give you a sense for why there's variety, some species have obvious visible differences. If you look closely at these zebras, it might be hard to see at the back, but the plain zebra has stripes that cross the belly. It differs from the mountain zebra and the imperial zebra, which their stripes do not cross the belly. You can see in the plain zebra, it's got fairly thick stripes. The mountain zebra and imperial zebra have fairly dense stripes. The point is there's obvious visual clues we can look to say this is a species that's different from this other species. In some cases, though, for example, the onager and the kiang, I, for the life of me, can hardly tell the difference. They're so visibly similar. But if you look at their cells and their genetics, they have different chromosome numbers. They have obvious and profound genetic differences, so they're labeled different species. Classically, species have been defined by their ability to reproduce or to not reproduce. It goes back to Ernst Mayr in the 1930s. The challenge, of course, there is with millions of species alive on the planet, we haven't been physically able to go around and try to cross all these various species. So there's 300,000 species of beetles. No one has been able to go around and try to individually cross all 300,000 species to see who can breed with whom can't. So that's why there's all these different species definitions. So what I said in the book was the way you evaluate my hypothesis It was to get the full accounting of the morphological, genetic, and reproductive separation in two candidate species species populations at two different time points. That's a mouthful of a word, but basically, mouthful of a sentence, but basically what I'm proposing is what you need to do is get everything that defines a species at time point 1, and pick whatever you want. How it looks, its genetics, who it can reproduce with, whatever. Just whatever defines a species, get it at time point 1, get it at time point 2. And if there's no change, this would be evidence against the number I just proposed. If there is a change, that might be an argument for the formation of new species. My prediction, I published my book in fall of last year. There was a paper published in January of this year that is directly related to the numbers, the 2.4 new bird species per year that I just told you. So January was future when I published my book in October. And this particular measurement of the rate of speciation comes from Exhibit A for evolution. Darwin's finches show up in textbooks as premier example of natural selection in action. Well, there's 18 recognized species of Darwin's finches. This is based on a paper that was published in Nature in 2015. What's been added to this story in Darwin's finches is a remarkable result, and this story begins in 1981. I'm going to show you a better image of these two finch individuals, or these two species, in a moment. This is a family tree. Circles represent females, squares represent males. So here's these lines here connecting them represent then their offspring in the second generation, third generation, so forth. 1981, a male of the large cactus finch, and you'll get a better image here in a moment, flew over to an island of the Galapagos where the intense study of evolution and natural selection was being done on the medium ground finch. So here you've got two separate species. The male comes over, mates with a number of females. Most of their offspring get absorbed into the resident population. But there's one lineage that by generation 3 here, there's close relative mating that results in offspring that stay reproductively isolated. They're building nests on the same island as that parent medium ground finch, but they're not interbreeding, reproductively isolated. That's the first thing that was observed. Second thing that was observed, and you'll see an image of this better in a moment, this lineage that's reproductively isolated is visibly distinct. They have a different beak size. Thirdly, the people doing the study, Peter and Rosemary Grant, British couple based in Princeton, New Jersey, they were getting the tissue samples. They have the genetic data from every individual in this pedigree, and this lineage is genetically distinct. So basically every criteria that defines a species was measured in this study, and the conclusion from Peter and Rosemary Grant's team in their January 2018 paper was rapid hybrid speciation in Darwin's finches, Science magazine, basically the Nature journal for the United States. Rapid hybrid speciation in Darwin's finches. So here's a better illustration. You can see here, here's a member of the medium ground finch population, so aptly named medium because its beak size isn't the biggest. Here's the large cactus finch male. There was a mating, and this big bird lineage, because it has a beak size slightly bigger than the medium ground finch, that lineage was born, new species. So what is this recorded event? What implications does this have for the predictions I made in October? Well, let's run the numbers. 11,000 bird species alive today. We ran that math, 2.4 new bird species per year. We compared it to the evolutionary prediction. But with 18 species of Darwin's finches, so they were brought to the attention of the scientific community in 1837 as a result of Darwin's voyage on the Beagle around the globe, hence Darwin's finches, that's their name. They were labeled new species by John Gould, 1837, that's 181 years ago. One new species of Darwin's finches has been discovered in 181 years. Well, 1 divided by nearly 200 gives you a number far less than 1. So, at first pass, this would seem to refute the number I just wrote. But think about this. The number I gave you was a global rate. 2.4 new bird species per year is a prediction that somewhere among the 11,000 species that fly around this planet, 2 to 3 of them are going to form a new species. And in this particular study, they've only been watching 18 of these 11,000 species, so we have to apply a correction factor to extrapolate it and compare it to a global rate. So the math you need to do is 1 divided by 181 divided by 18 times 11,000. That's the correction factor. So let's put these numbers in a row. The evolutionary prediction of 1 new species every 3,200 years is a rate of 0.0003 new bird species per year, globally, very slow. The creationist prediction is 2.4 new bird species per year. And if you do the math for Darwin's finches, extrapolate it to a global rate, one new species divided by 181 years, divided by 18 times 11,000 gives you a result of 3.4 new bird species per year. That's pretty close. In a sense, it's like me predicting that the Champions League football is going to still be played in the year 2050. And then me saying today, I'm going to predict for you the two teams that are going to play in the final. And furthermore, I'm going to predict for you the final score. And then we live our lives, we get to the year 2050, and yes, lo and behold, the exact teams that I predicted are playing in the final, and the final score is correct, except that I'm one goal off. You said that was a pretty good prediction. That's basically what this represents. So, two illustrations that the advances of creation science, the modern debate in which we now find ourselves, are leading to successful retrodictions of predictions in multiple fields of biology.